So, okay, just Tariq, I hope that wasn't, I know that was an overload, but because of course he's deep in the field, massive experience. But you get a sense, and this is really fundamentally to me what's the most important thing here is I want you to be sure to get a sense of um, what's of the confidence of the people who have the experience in this field. Like I've heard people go, even in our team go, well, maybe, and we don't know if this will work. And it's like, no, I know this will work. I've been doing this 17 years. He's been doing this 27 years. There's not a question of this will work. You might end up tuning something, but it'll work. So back to this original thing, there's all these different topics, and I realize that you got to think of these all together, right? It may not be systems engineering, it may be project management or whatever, but you can't, for example, in this field, like Kerry, he's not an engineer, okay? He's not a licensed engineer. He's what we call a designer in this field. And you need the people who have the right experience to pull this whole thing together. That's a key. And the only barriers at this point, I think you can get from the sense of what Kerry presented, they're not technical. The thermals out there, it's just a managing the thermal, modeling it, figuring it out, and then tweaking a system. The problems are all other things. And then I saw this just in the news. Actually, Ken, Phil, I'm sorry to pick on you, but I saw this article that Phil wrote. And it mentioned that Harvard is still trying to figure out how to decarbonize by 2050. And I just go, oh, come on. Clearly, everybody's talking to the wrong people because there's no way you couldn't decarbonize by 2050. You'd have to just be really not trying to do it with the technologies that we're talking about. And with that kind of climate thing going on with the ocean temperatures and whatnot, this is just not a problem we can all drag our feet on. So I just want to throw that in there. And like I've said before, we sort of got used to this whole thing of where we're paying the oil companies. The money is all there. As you saw from Kerry, these people are putting this stuff in and they're saving money. They're actually making money relative to now. And what they're really doing is they're taking some of this money that right now everybody's shipping off to the fossil industry and just saying, no, we're going to invest in the equipment, the geo, the equipment, the solar and whatnot for industry, maybe some other high temp stuff, and maybe some deep bore. And we can pull this off. It's all there. The capability to pull that off is all there. I just want to run these through just to keep them in your mind. The idea of eliminating all the fossil in this system, except for maybe airplanes and some ships, is all there on the table now, even for large construction equipment. And showed this to you before, 13 years. It's happened before, massive, complete change in 13 years. It can totally be done. So why is this happening? Just to understand why this change is in fact afoot. You see this yellow curve? This is by Lazard. This is some guys that if you ever want to know what's currently going on in the energy business on any level, these are consultants who corporations pay a lot of money to put big reports together. And they will release their report like after 6 months to the public. So this is the graph of all the power generation technologies in the country. Nuclear, see nuclear is right there at the top, gas peaking all the way down to wind and solar at the bottom. Solar, this is the curve of solar. You see this exponentially declining curve, solar, starting in 2009. That's because the government figured out that this was a total winning situation back then and invested a bunch of money to start getting solar into bigger production. And it just broke the ice and broke the whole thing open. And it's that, so that's this curve, 2009, 10, down to now, okay, somewhere in here. I'm sorry, these graphs are a little old. The reason that I see this as a done deal, and it's only a question of how long it takes for people to get on board with figuring out this new energy market that's decarbonized, is because I've watched this thing happen. There's the solar curve, there's the wind curve. Now here's the battery curve happening now. And the battery cost curve, these batteries are going in like, you see every couple of days, there's another giant battery going in somewhere. And I'm sure they're not even reporting on all of them. This is exactly what happened with microprocessors in the 70s. I was in high school in 74, and the Intel 8080 microprocessor, one of these 50-pin things that was like the first real microprocessor computer on a chip, was, launched, I don't know, it might have been 73 or something, might have been slight before that, but they were in 74, they were like $250. I made it my senior project because I was watching the price come down. By the time I bought one, like in 74 sometime, it was $125. It had already dropped 50%. And now that is clearly what started the information age. And along the way, a couple of things have gotten added. The internet, the TCP layers of the internet and stuff got added in the 90s. And now we got fiber and everything. But what these exponential curves are about, this was Andy Grove. He's one of the three founders of Intel. And so the whole thing, like Moore's Law, you've heard of Moore's Law, things in the computer industry keep doubling and halving in price and all this kind of stuff. That's another one of the three founders of Intel. Andy Grove wrote this little book on called Only Paranoid Survive, on how to deal with inflection points. And that when you see an inflection point, you should jump on board and realize it, and realize the world has changed around you, because, you can't fight those fundamental changes when things go really wild and things drop in price by 90% like solar has and stuff. That is a fundamental change, and it's going to fundamentally change stuff. And you can see it's totally happening. I mean, this is what's happening with battery storage right now. It's just unbelievable through the roof. This is what's still happening with solar. It's still exponential. I mean, we're being constrained now by like the limit of the polysilicon market. Of actually mining the materials is the only real limiting factor going on. And I just want to remind you, this whole thing of like, you invest in the equipment, you do the right thing with the heating system, and you'll get better. So this is a conventional, this is with geothermal, and then you invest in solar and add solar to that. And the bottom line is you end up making money, even in a school. And this is being repeated all over the place. And you guys are going to go see one of these net zero schools here soon. And I don't know about King Open, but a lot of these people are doing this all with just these individual units, which essentially are a distributed network in the school. A two-pipe ambient loop just runs around the ceilings of the hallways, and you hang these units off with pumps built into them, and they actually have no central pumping even in a lot of that situation. Okay, there's a great video at DOE if you're ever inspired. I'll try to get a link to this posted on Canvas with Susan. So it's so interesting because even people who are kind of smart, this is the International Energy Association, but they are historically oil and gas, okay? And so they have these I wouldn't say, like a hatred toward renewable energy, but I think they just don't have a grasp of what exponential inflection point change is. So year after year, the solar starts going up, PV additions starts going up, and year after year they go, oh, well, it's gone up this year, but it's going to level off. It's gone up this year, it's going to level off. It just keeps going on. And even now, after this graph, so this only goes to like 2018, it keeps going on. This is what's actually happening. And this is what they keep predicting. So this is what I'm just trying to say. Be confident. This change is afoot, and it's not slowing down. It is going to happen. And all of the people who haven't caught on yet, we just have to run past them and just mull over them, I guess, because they will catch on, and they are, but it's clearly taking them a while. So this technology of a jet engine, that's a jet engine, which is what MIT has in its central plant. It was a great, wonderful technology for what it was and is, which is a fossil fuel-based energy source. Perfect for that. Might be perfect for peaking and dealing with odd situations that happen. Something goes down, something this or that, forever could be. But it is essentially functionally obsolete now. You would never go and like buy another one of these and put it in. Although there's a few industries doing that, but not campuses anymore. So I'm sorry, I got a copy here and something. So back to the barriers, building decarbonization barriers. Why wouldn't you do this stuff like Carrie presented, these ambient loop systems? they'll massively save money. There's huge rebates. They're less expensive to maintain, less expensive to replace. And any of the stuff you put in the ground is going to outlast your buildings because this pipe, nobody has any idea how long this pipe will last, but it's lasted its entire life, which is like 60 something years at this point. And so, why wouldn't you do it? Because it's more complex and we just got to keep teaching people. We got to keep telling people about this and getting them in touch with the right individuals who have the experience. The barriers are all untechnical. Anyway, I just wanted to point out, so we, back in 2016, the reason we're kind of here is back in 2016, we came with this knowledge. I'd been hearing these guys talk, we've been hearing these guys talk at the International Ground Source Heat Pump Association conferences. And, once I saw that these schools are making money, it was like, okay, I can see this is a done deal. This is a concept breaker. And so we came in 2016 naively thinking that we could go present this to MIT, and we got selected by the faculty to get this award for this in 2016, the Climate Collab. And you can see from this little simple drawing, we sort of drew just basically the same thing you've seen Carrie draw. You got a network, and you got all the buildings and stuff hanging off of it. Well, here we are 8 years later, and I think finally this year we're finally achieving some kind of breakthrough. And it's taken forever. And we even gave them all these people. Look, Carrie Smith. You recognize all these. Now Susan's taken the course from Ed Lorenz. You just met Carrie Smith. He's met Carl Oria. And the only person you haven't met here is Don Penn, and he's the guy who did the Lady Bird Johnson School and said, get rid of the steel. And now the industry doesn't use steel.
So Rick recommended all of these people who are leaders in the industry in 2016. It's amazing.
2016, put it all on the table. And really the program that you're going to learn about next year, the proposal we've got on the table is really unchanged from 2016. It's just a little refined. So even back in 2016, you see, this was a graph of the economics and, I'm sorry, what's going on with the mouse here? Here we go. There we go. Even back in 2016, we were showing that geothermal had passed this effectively free moment, but PV had not. Well, believe me, PV has passed that effectively free moment at this point. So in 8 years, it has totally moved past this, and batteries are moved like down in here. These things are all have people investing in batteries because guess what? They make money. That means they are below this, cost benefit. These things are rapidly moving down this technology progress curve and becoming economical, just in 8 years. And a key thing in this business is, like I was mentioning just before, it's that you need the designer, the person who understands how to model these things, these systems. They're more complex. It's not the guy who draws the plans that you really need. Why's the mouse disappear? It's not this guy that you really need. You need the designer. And that's what the missing piece is, because like people, for example, the administration at MIT, point no fingers, because this is literally everywhere. The people we talk to in Asheville, the people everyone in this business talk to, it's the same issue, is that you go and you ask your engineer, well, what about this geothermal thing? And they don't know about it. So they give you answers that are whatever, incorrect. Anyway, this is from the standard that's coming out. So if you all ever end up working with any governments or whatever on these kind of advanced thermal systems, this is how you guarantee that something gets done right. You cite the standard. And this standard, the new version of the standard, the ballot out's right now, so it'll be out within a month, I think. Question came up last week about St. Patrick's. So I thought I'd start here with New York, and let's just start here with this top one. So one of the advances that's happened in this industry is that this guy, Bob Wyman, was a Google plant. He got supported by Google to show up in the industry and started learning from everyone, smart computer guy. And so this is now the mayor of New York, former mayor of New York, signing a resolution that made it so that all new New York buildings and major retrofits had to use geothermal unless the engineers could show that something else was more economical. And the reason for this was because Bob figured out that the issue here was, like we were saying, non-technical. All the barriers are non-technical. So this basically said, okay, we're taking this, all the issues are non-technical off the table. We're just going to mandate it. And then you guys figure it out and come up with something else. So that was a major thing. And that's kind of like the first step. If you want to decarbonize, what essentially what you do, this is about geothermal. And I'm really always not trying to focus on geothermal here. This really is about advanced thermal. And the number one thing to do is to say, look, people, go figure out how to decarbonize these buildings. Then it's on the engineers to figure it out. And that is really the right thing to do. You just
Can you
mandate
just
it.
explain the difference between geothermal and advanced thermal, so people understand how you define your terms?
So geothermal is just one piece of advanced thermal. Advanced thermal is you use whatever resources you had. You notice that last graphic that Carrie showed that had all those different thermal sources. You might have wastewater. There's always a lot of heat going out in wastewater. You've got municipal water supplies that you can use. That one of the things we were going to see in our pilot project. You might have surface water, lakes. You might have an industry next door that's got waste heat that you might have a data center. Think of every one of these computer servers everywhere, all over MIT, and everything produces a lot of heat. And right now, people are having to cool those. Well, why not just grab that heat and put it in the ground, or put it in a thermal storage, put it in a tank, put it somewhere? And that's what advanced thermal is saying. No, it's not dogmatic about anything. It's saying, what are all my options? What are all my sources and sinks? Things that I can pull together and come up with a decarbonized system. Is that good, Susan?
Yep, that's excellent. Thank you.
So this one here is just an interesting one. They took a drill rig out on a ferry out to the Statue of Liberty. This is a standing water column like Susan has, but I think it's more like 1,500 feet deep I think it's two of them for the visitor center there. And that's geothermal. That was an interesting thing. St. Patrick's, I think I've got some stats here on it. St. Patrick's is 10 wells, 2,200 feet deep each, and they're standing water columns. It was done in 2017, came online in 2017. And it's, I just got a few stats here. You can look at these later in the slides if you really want. But it was, it's completely successful. And in Manhattan, you've got very little space, so you do a different kind of thing. You do these very deep bores, and standing water column means that you bleed off a little bit if they get out of temperature. It's one of the technologies. Folks at Susan's class also asked about the finance, so I thought it'd be good to show you this. This is, who knows if the IRA is going to survive? We'll see. However, the vast majority of the money in it has gone, and I don't know about the vast majority, but for sure the majority has gone to red states, so it just might. As an example workup on the spreadsheet from Climate Master, one of the major manufacturers, the people who make the most commercial geothermal equipment. So this is, for example, for non-tax entities, so that's like state governments and schools like MIT. And we've got a geothermal system here that was going to cost, it's an example of 1.1 million for conventional and 1.6 million for geothermal. So that's a $500,000 additive for the loop field and such. And there's some utility rebates, so that was going to cost 500,000 more. But oops, I thought I had something else in there. I lost it. It was in Massachusetts. This is actually better in that this there's like a several $100,000 rebate, so $4,500 a ton right now in Massachusetts for pure geothermal. And these are the tax credits in the IRA. This is the Inflation Reduction Act. There's a 30% for geothermal, solar, wind, all those kind of technologies, all those renewables. There's a 10% for domestic manufacturing, of which all the people who manufacture geothermal in this country are in the States. And there's a 10% if you've got a brownfield or something like that. That's actually for anyone who's even in a census tract around a power plant that used coal and was shut down. We have that here in Asheville. And the bottom line is, in this case, with all those figures, there's the addition is $850,000, which is more than the $400 something thousand. So there's a net savings from day one. is the way this works. So this is a profit from day one for anybody who can claim this. And it doesn't matter whether you're a nonprofit or I think I have another screen here, a for-profit with taxes and whatnot. With this IRA, a lot of these geothermals are profit from day one. And that's exactly what the government was trying to do, is to say, let's juice this system just a little bit, get it going, get people on the road to decarbonize. And I think it's happening, because I'll tell you, the geothermal business is like the volume got turned up bad. So that's good. If you want to learn more about these things, there's a tax compendium by a guy in Boston who's a tax attorney. He has a list of all the credits. You can go there and get it from him. He'll gladly email it to you, or it's on his website. And in the geothermal business, if you really want to know about geothermal and decarbonization, building decarbonization, that kind of stuff, this guy, Jacob Golden with Energy Tax Savers, he's the go-to guy. He presents at all these conferences. He really knows all this stuff, and he's got package deals and stuff for people to do, for him to do the accounting for it. Anyway, there was another question about.
Yeah, you got 5 minutes, 7 minutes, maybe.
Really? That's all?
Yeah,
Okay.
yeah, because we have to get there by 4 in order to be able to have daylight on the roofs when we see the the solar PV.
Okay.
And down to the cars, and we have to find our way there. Yeah.
So another barrier is engineers who don't know what they're doing. This is an example of a job we got doing the chancellor's house at university. And this engineer, this thing of digging all these trenches like this, it's insane. But that's what this engineer did. Some more insanity of the engineers who don't know this stuff. Here's an example of a well log for another job. And you'll notice water. Okay, so there's a lot of water coming out of this ground. And it's only I'm sorry, I've got this thing blocked. It's only 300 feet deep. So then the guy goes and specs the job at 450 feet without having even drilled a 450-foot bore. And the job turned into this. So this truck over here is drilling air rotary and blowing air into the loop, the water down there at depth, and it's geysering up over here, and you can see rocks. There's rocks coming out and raining down on this truck, sitting on top of the truck. It's the most insane thing I've ever seen. It's a total disaster. And the disaster was because the engineers just go and do their thing, and without actually learning about this field, and they caused this. This poor driller lost his shirt on this. It was bad. We lost our shirt on this too, which was bad. That's collapsed, wet, muddy ground. Just, you can't dig in it. It's just a disaster. Anyway, I just skipped this. I'll show this next week, maybe. What else do I want to show? Oh, wait a minute. I want to show, some of these things are a real mess. I noticed this is a shot I just got from Tunja's thing. I just copied it off. Notice how this can be a mess. This is another one of the issues with geothermal. You really want to pay attention. You want to make sure you've got everyone on board and you know what's going on in terms of controlling mess. This is the kind of stuff you don't want. You don't want this. So here, I'm going to skip this part. I'll do that next week. So I just want to point this out. So in the briefings you just saw, there's multiple paths to these districts. This is what Kerry was presenting, is this one pipe approach, where you got one pipe circulating an area. And it's he really thought it through, because a lot of the energy used in this is in pumping. And so this has a lot of merit. But there's situations.
Bottom left, is that correct?
Say again?
You're talking about the bottom left part of your image.
Are you not seeing my mouse?
No. Oh,
Shoot. Really? You don't see my mouse?
Oh, well. Your mouse. Go ahead.
Bottom left is Kerry's one pipe approach. It really focuses on reducing pumping energy. The top left is one that Tunja just showed, and it's a 2-pipe loop. So you've got it's send and receive, or you can even designate them as hot and cold, and you can always reject the heat to one and suck the heat from the other. You can pick your patterns. My point is, there's a lot of ways to do this. There's no dogma. There's no one way. And this is why they have to be designed. Let's just go on. Then there's some other really out there things. This is in Norway, off a fjord. So you know how cold that's got to be. And this is a giant heat pump in this building. And giant heat pumps, big electric heat pumps. And it actually produces, they produce some hot water out of this thing, some really hot water. It's not very efficient. See, now this is temperature out, temperature in, and these are the efficiencies. And I just want to get this graph. This is almost a generic graph about heat pumps. How if you're close to the temperature, so let's say if I'm coming in at 40 degrees and I'm going out at 60 degrees, I can get some really good, some really good efficiency out of the thing. But if I'm coming in at Boston Harbor and I'm trying to produce really hot water, then the thing is barely going to work. So understanding this curve about heat pumps, this is a particular model, but understanding this curve and how these temperatures relate is of course critical. So you can't, for example, one of the things that's happened we've seen lately is that somebody asked engineers, well, can you create steam from geothermal? And the answer is no. I mean, you can, but it's not efficient. So if you're going to decarbonize, you got to separate these concepts. So if you're going to decarbonize, then efficiency matters. Okay. So I know this is a mosh and stuff. I just want to kind of give you a sense of all these different aspects so you realize there are people who understand this, and those are the people that you have to have involved. Because unfortunately, if you don't understand it, you don't. Here's a great example, Susan, of not much geothermal. This is a giant IKEA store. You can see the size of the cars. It's very big, 3 stories tall. It's got like, I don't know, like 4 or 5 restaurants in it or something in Denver. And the problem here is not getting heat. It's in Denver, so it's cold, right? The problem here is they got too much heat in this building. A giant box with a bunch of restaurants, they have too much heat. So this entire huge building has something like 27 geothermal bores. 27 bores is like nothing in a building like this, but it's got this giant thermal radiator because getting rid of heat. So this is under one of these concrete ramps, I think around the back here somewhere. So this is in the concrete, are these PEX loops as the thermal radiator to get rid of heat. So there you go. There's another source, see? A thermal radiator. In Massachusetts, what you would do is you would put loops under all your sidewalks, under your handicap parking places, the crosswalks, stuff like that, to do snow melt. That's how you get rid of heat. So here's an example, another example of another campus system that did a district, sort of. But they did a 4-pipe district, not an ambient loop. And so you got this campus. It's look at this. And so they first of all, something worth knowing is, well, they built this giant icon to central plant, okay, which is sort of one of the things that's been proposed at MIT. Giant tanks and a big central plant building. Yeah, it works, but what is this place? So Boston has an energy pattern like this. This is your daily average temperatures and what percentage of the time. You can see Colorado Mesa has basically a very similar pattern. Stanford has that pattern. So it is completely not a pure location. It is not a corollary in any way to Boston. And yet, that kind of big system is one of the things that's being proposed in Boston. You can see that most of what you need, this is the heating and cooling. So this is cooling on top, heating on the bottom. You can see that most of the time, the overlap here is in the dark. That's dehumidification, simultaneous heating and cooling. San Francisco, that's what you do most of the time, is you have to dehumidify things, simultaneous heating and cooling. And so if you go in with a 4-pipe system, you have to build that much pipe. You got to serve all the way to that peak, and you got to serve all the way to that peak. So putting that 4-pipe in, Stanford put in 20 miles of pipe, 20 miles of new pipe, buried in trenches and in new trenches. So that's a lot of campus disruption. For the central plant concept, it costs $485 million. And they say that it would save 420 million over 35 years. Well, saving 420 million on a 485 million, you add the discount rate in there at all. Excuse me, discount rate, because of course you discount everything in the future money-wise. Basically, this system is just losing money. And that's fine, because that's fine if that's what you want to do. But it's just so out of step with what this advanced thermal world is doing. And so there's another example of this is what putting in miles and miles of pipe does. You just get these giant digs and stuff, which you really don't want. So that system is that's the 4-pipe version. The 2-pipe version is going to be something more like that. That's how much pipe you may need to have. That's how much thermal you need to support, because these peaks are going to get supported in just the inertia of these systems, because peaks are usually not very long. So you don't need the root capacity. You heard Carrie talking about that, how you've got really a much smaller amount of net system installed for peak capacity once you get these diversified 2-pipe systems involved. So that's what the advanced thermal is about, is that kind of a difference. And at MIT, this pipe already exists, so it's not needed at all. So that's the existing chiller loop at MIT. This is what the difference is at MIT, and I think I'll show this again next week. This is what the difference is. This is what we are proposing. You have to add a line here, a couple little lines here, and one line out this way, an ambient loop. And all of those same lines would have to be added in a 4-pipe system, like is being advised by others, by engineers, for MIT. So all that has to go in no matter what. And for a 4-pipe system, all of this red has to go in as well. And not only does all this red have to go in, but this red has to go in as steel, because they're talking about high temperatures. And that is massively expensive, and just is the real thing that which will probably shut down that approach, because that is a waste of money when all you need are these few pipes, and you don't need them as steel. You put them in as HDPE or polypropylene, these fusion welded pipes that this industry uses from the oil and gas industry pipeline business. That's where it comes from. So we did some tests of this little building, this spot right here behind Kresge under the now music building. This particular bore, we had a good log to depth on. You can see I've cut it up here just to show you, but you can see at 10 feet depth, 25 feet, 50, 100, 120. They hit bedrock at 120 feet. So MIT is sitting on a pile of totally wet, saturated clay. That's what it is. It's a coastal estuary. And with a little sand on top and a little bit of fill on top. People think of it as like, oh, there's so much fill. It's like, oh, no, there's not. That was a tidal river basin. So it's not that deep to what it was before the fill. And so based on that, there's other approaches. Actually, that approach we now believe isn't the right one. So I'll skip that. So after what Carrie said, I think we've been proposing this based on research out of Oak Ridge National Labs of using thermal batteries in this 100-foot overburden. So incline drilling, we'll probably end up doing some incline drilling. I'm sure we'll want some of that good solid rock kind of thermal conductivity. But there's this giant opportunity, especially in what you saw Carrie was talking about, of just storing some energy to be able to retrieve it when you need it. And that's what this is the next generation in this field. So think about this field is we're kind of in this field at this point of like maybe 2000 in the computer industry. By 2000, we had processors, the good processors, and we had the internet, and we had memories were cheap. And I'm pretty sure YouTube was rolling and things were really rolling. But think what wasn't there yet in 2000. Well, cloud, doing everything on the cloud was certainly not there in 2000. These giant server farms and everything on that scale, that's here now. And of course, fiber has been a big part of that. The broadband and everything has been here, and that fiber was not anywhere near that. I mean, that's been a whole progress in the computer industry. From literally, I used a 300 baud modem when I got to college at MIT. I left college with a 1200 or maybe even a 5600 baud modem. And then it was, then you had to get a long way before we started getting fiber out places. Cable was the only way it was done until before that. Now, everything is total broadband. So you see this progression in AI, and now AI. This industry of thermal is on that kind of a progression as well. And we're kind of at the 2000 point in the computer industry progression. So there's things like this to come. And there's probably a lot more to come as people get creative, like the angle drilling and whatnot. There's a lot still to come in this field. In the course of trying to help explain to engineers what the next generation and the next generation after that, Gen 5 and Gen 6 of HVAC systems for the 2050 decarbonized grid will look like, we've created this graphic. It's a bit complex. So in this brief presentation, we're going to build this graphic and help you understand what it is, why it is. So we used to call it 5 kinds of HVAC. Now we think it really should be more closely called cost-effective HVAC decarbonization for the 2050 grid. So this is a byproduct of work we've been doing with the MIT D-Lab, and of course taught by Susan Murcott and working with her students. And this course, we gave a presentation in May on HVAC design for the clean energy grid. And this is an extract from that presentation. I'll show you a link to it if you want to go see it. Tell you who we are. We're a combination of things. I'm a computer engineer by training. Career A. Career B is in HVAC and in developing products in this field and in being an expert in the geothermal heat pump field. And we just do a lot of stuff, and I'm on the Binational Standards Committee. So I know a lot about this stuff and can try to help convey this information. And in that longer presentation at MIT, we resolved these questions. Will it cost too much to decarbonize? And you go listen to that. No, it won't. Definitely not. And a lot of people say we don't have the technology to decarbonize. And for buildings, that is bogus. It's just not true. There are a few things like Bunsen burners and all, but I think we showed that people have solved some of those too. I don't know what else there is on a big college campus, but I think in general, we have all the technology. And then there's the question about how much power is needed to do this. And there's no question some more power will be needed, but it's not going to be some dramatic amount. And the thing is, we can't prove that yet because we really need some better modeling and whatnot to be able to pull it off. So we're developing that now. And you can see this whole presentation at that link at the bottom of the screen if you'd like, including a piece before ours where the students explain the modeling technique. Just so you know what geothermal is, everybody knows, on a very hot day when it's hot outside, you got to use that 90-degree air to try to cool your house. And when it's cold outside, you got to try to use that 25-degree air to cool your house with an air source heat pump. Well, geothermal uses the ground. And the ground is a very stable temperature that vacillates a little bit around your average air temperature where you are. So your average air temperature determines that ground temperature. And it all uses just basic equipment like that. Looks like a furnace box, like any other furnace box. Nothing magical. Here's an example to show you how this field is advanced. This is a middle school done a decade and something ago in Texas, beautiful school. This engineer set out, after 100-something geothermal systems installed, he set out to figure out how to do a net zero energy system. And so he gives some advancements, and I cover that more in the longer course, so go back and look at it there. But basically, it's all the same box, just the horizontal mode of the box up in ceilings. And this is what the economics model for that installation worked out. He figured out, see, these two bottom lines are the conventional line for what they call 4-pipe, chilled water, hot water, the geothermal curve for economics, and he figured out how to do them in Dallas for basically the same money. So that's not true everywhere, but it's kind of true right now with the IRA tax credits everywhere in the US. Now that makes a bunch of money. So that would save you $2 million over the course of 20 years anyway. And apparently this system's worked a little better than they even thought. Add solar at the time, 2.7 million for those rooftop systems you saw. And that saves you over time 9 million in 20 years. And that's not even the full life of the system. It's already effectively free. It already turns a profit in 20 years. And it's not even the full life cycle cost, which is even better because the ground loop in geothermal is going to last over 100 years. That's the official life. Nobody knows how much longer it will last, but it's some long time. Here's a study done by Department of Energy under the NREL, Renewable Energy Lab. There's that school in Texas, just outside Dallas, and you can see it actually produces more energy than it consumes over the year. So let's start building this graph. Now, these are all the heat pumps we're going to be talking about, all the way from air source heat pumps over here, the geothermal heat pumps over there, and especially geothermal and these cold climate heat pumps, the things in between that are the high end right now of air source heat pumps. A lot of people know them under the title mini splits, for example. They're just a high end air source heat pump. In this graphic, you start to see first off that the fossil on the right there is just not a carbon solution. It's never going to be a carbon solution. It's never going to be decarbonized. An infinite time to decarbonize. This curve shows the installation costs in general, although right now the installation cost for the IRA tax credits is not really more for the geothermal. It's actually the same as air source heat pumps, maybe even better. And so that's the installation cost. And you can see it generally goes up to the more advanced systems on the left. And then there's the operational cost, which you get it, you pay more in your system. It's got the earth as the anchor. It costs less to run the geothermal than it does the air source. So let's give them another little couple dots on the graph on the development here. This is the Engineers Association, ASHRAE, Mechanical Engineers Association. They decided to take one floor and make it geothermal and one floor and make it air source heat pumps to sort of settle the argument that was going on, which one's better. And this is the actual data that they took off this. Xiaobing Liu and Professor Spittler at Oklahoma State and at Oak Ridge National Labs did this data, and they recorded a lot of excellent data. Now, I happen to know on this, so this is the curve of the ground loop in blue, and the red is the air temperatures. You can see it's got an annual cycle. Now, I happen to know that the average air temperature in Atlanta is more like 54 degrees. So that loop is running a little hot. It should be running down here. That would be better. That would produce a more efficient solution. So this wasn't quite engineered to the perfect stage of what we do now in this field. And so this, how you tune these loops, this is what's taught. There's a specific training called the Certified Geoexchange Designer, CGD, of which I am, and maybe, I don't know, 1,000, 1,500 people. Your engineers, if they took this training, would know a whole lot more than they do now, that's for sure. And so that's where it should be running. And there's ways that you do this. You tune it by wasting heat out of the system in the spring when it's very cool in the evenings and the power is very cheap. So there's specific ways you do this that are known by the people in the field, not known by others. You put in maybe ice melt loops under your sidewalks and under your parking lot areas and stuff. And you just use those in the spring to waste energy or when there's snow and ice. It's an annual cycle thermal battery. That's the key point. This thing varies annually with its load. This big chunk of earth under a building. So let's pull that together here. And instead of thinking about these as heat pumps, let's now think about what the thermal battery is involved here. So for example, in the air source heat pumps, you have no thermal battery, and in the ground source heat pump, you have an annual thermal battery. So that's a spectrum of end to end on what the limits are here, using the earth and using nothing. So again, Inflation Reduction Act, price, the installation cost is actually level. So this is some data, the analysis of the data from the ASHRAE building. And you'll notice this is the VRF air source, high-end air source solution up here. This is cost versus outdoor temperature. So this is looking at the temperature domain. This is the summer peak over here and the winter peak over here, coldest. And you'll notice the geothermal system runs at a lot lower level. Of course, as we showed you, that battery should be tuned better. And so in reality, it should be running about like that is where it should be running. But still, basically 2 to 1 on the power. So let's overlay what a basic air source heat pump runs as. And that thing is much less efficient than the VRF. And the big deal is that when it gets really cold, down to maybe below like 25 degrees or so, these things will cut into electric strip heat. And that is a much more expensive thing to run. What they call coefficient performance run, just electric strip. we'll never be able to build the grid for that. I mean, you can't build a grid for 4 times the peak when you can build 1 times the peak, so it will never happen. And in reality, even building the grid for the VRF versus the geothermal, it's going to cost an awful lot more. We don't know exactly what this trade-off is, because there's installation, which is costing more right now. These batteries are 3 times as much electric versus this, but it's a little more complex, needs to be modeled to understand it perfectly. So looking at that on here, first of all, the air source heat pump, there's no way we're going to build the grid for that, so it has an infinite time to market as well. And then there's this becomes, including that is not a feasible solution. So those are all not feasible zero carbon grid solutions, zero carbon society solutions. The air source heat pump, the high ends have a coefficient performance of somewhere around 1.8 or so in the winter peaks, maybe 2 in some circumstances, depending on where you are. So they're twice as good as the basic units. The geothermal 4 times as good. And that's why this operational cost curve goes down like that. So looking at the grid, there was a study done in Canada for the Air Conditioning Refrigeration Organization there, and they found that using even those high-end cold climate heat pumps, the grid will cost almost twice as much if you use all air source heat pumps versus all geothermal heat pumps. And going back to this graph now, that creates points like this. So even with that, and we start to understand that even with all these air source heat pumps, it's still going to be very expensive to build that grid. But they're going to have a much higher cost to the grid than if all geothermal heat pumps. What we're going to show is there's another class of batteries in here. Let's just call them other for now. And they are going to produce something better. And we're going to show that they produce an even better cost curve, that we can do better than just conventional geothermal. So we know there's a lot of wind being built. Here's what wind looks like from the energy delivery point of view. It's chaotic. It goes up, it goes down. You have times with massive amounts of wind, time with just moderate amounts of wind. And then if you draw a line here of what you expect to get from your wind, you'll see there's a lot of blank periods where you would get much less, sometimes 0. And you got to watch out, because this will coincide with when a snowstorm, you'll get no sun on the PV panels and you'll get no wind. So wind, even during a day, you can see it's chaotic during hours of the day. Switching to solar, you can see solar is chaotic. It's up and down. It's got periods of overcast for days. But we right now have built enough solar that we've got almost all the power we need certain times during the day. And in fact, by 2050, people expect that we're going to build double what we need to get the whole grid to operate. So there's going to be a lot of excess power. There's going to be some periods of really expensive power that you don't want to have to buy it. And there's going to be some periods of really cheap power when you want to be able to use it if you got some way to use it. Well, this stuff has already happened in California. They've already hit 0 and beyond for their power production. They're already cutting solar off the grill, what they call curtailment, where they say you can't connect to the grid. That's already happening all the time, even when you would think we still need more renewable energy, but it's not a perfect picture. And right here you can see in these the marginal pricing for power goes way up and way down depending on where you are and the time of day and where the sun's shining. And here in Texas, for example, you can see in up here in the western zone versus the eastern zone, they're through 2009 and 10 even, there were all kinds of periods of negative cost of power from wind. This is a long time ago this started. It's just getting worse and worse. And this you can see from much more recently in 2021, a period of some really low, like cheap, better than free power is in like below 0 because they had too much on the grid, and periods of expensive power in different areas. So this whole thing of power fluctuations is a big deal. And that's where these thermal batteries come in. They can store the energy. So if you can get really cheap power, you can use them to store energy. And so those thermal batteries, first off, there's what's called water tanks, and people have been using these for a while, especially in summer times to store up cold at night and then use it in the afternoon the next day. That's been used for a long time, but people think, oh, well, that's just a way to store cold. It's like, no, it's not. It's a way to store heat and cold with heat pumps. So that's a day-long battery. That water tank is a day-long battery. And to show you how these match up to an analysis we did in these points match up to an analysis we did in Asheville. This is the real load of the generator at Asheville from Duke Energy at the winter peak one year. This is what you'd expect if everyone electrified around here. A lot more people use electric already around here than some other places, especially up north. Take a typical solar curve, map that over. You might get this kind of a curve from solar during the winter peak, because only during the day are you going to get some savings, not at night at all. With just a water battery tank, you can get this kind of reduction in the peak loading curve, and a very dumb, as you can see, it's not very well done, a very dumb algorithm I just did in a spreadsheet to prove the point, how you can lower the curve back to where it is already now, just with a water battery and a little bit of electric battery. And then how you can get with geothermal get even lower. So how these match up here? Well, there's the water battery. There's the air source heat pump by itself over there. There's the water battery, and there's the geothermal battery. So there's sort of a grid applied real example of what this graph does. So on here now, that other, what is that really? What are those things? Well, here's one example. This is a type of battery designed by Dr. Xiaoping Liu at Oak Ridge National Laboratories. That's he's got one of these installed. I made a couple of these installed, but he's got one in particular at University of Illinois, Champaign-Urbana, and it is 2 feet wide and 20 feet long, I believe. HDPE, basically a culvert stuck down in the ground that has a water battery with some phase change inside, and he's got pipes coming out of this several different ways. And basically, this is a 3-in-1 battery. It's a water battery, it's a phase change battery, which will store longer, and it's a ground battery. So it's all 3-in-1, which is very cool. And you could size the different components for what you want. You can create different sizes. You can put in more of them. So that's one way people do this kind of stuff, or will do doing this kind of stuff. And there's another way people use these geothermal systems. They can design fields so that you put all the hot in the middle, for example, and you put all the cold on the outside. And you can design these fields that are gradiated, and you can get better, more efficient recovery of your energy out of them. So there's a lot of variability in this stuff, a lot of engineering that can be done by people who know this, but there's only like 1,500 people who know this stuff at most. So we got to figure out how to get all the engineers on board. So there's those batteries, and they're tuned is the idea of design a tuned battery for your situation, your renewable power fluctuations, your weather fluctuations, your building usage fluctuations. The parameters include, for example, the storage capacity, which ranges from huge to limited, and the bandwidth. So the storage capacity, the water tanks are very limited bandwidth, whereas the ground loops are huge because you got this huge chunk of rock involved with your system. And the bandwidth, in other words, how fast can you get the energy in and out? Very fast for a water tank because you can just pump the water right into your heat pumps. Very low for the ground because you've just got this one little loop in a 20 by 20 big chunk of ground. So these things are all design parameters. And the reality is you've got to figure out how to do that. And here's the example, conclusion of if you took that 3-in-1 battery Dr. Liu did, phase change plus ground plus water, that should be able to produce this kind of an optimum point. A properly tuned one should be able to produce this optimum point for heat pump storage. A ground coupled, but also water battery combination. And this produces what we would call the ideal goal cost, the ideal overall maximum, the minimum grid cost to get to zero carbon, and the minimum installation cost to get systems that at least a large percentage of them need to be in this class, in this or this class, or we're not going to be able to build this cost-effective grid. So looking a little bit different at methods. So this tuned thermal batteries and designing how much water battery, how much deep geothermal design factors on the right here. Here's kind of a list of what all's involved. There's the local weather, there's which technologies you're using, phase change, not, water, this, that, different grades of heat pumps. What's at your physical site do? For example, at MIT, they have some very poor rock 100 feet down, and you can't really drill it cost effectively, so you just don't do those deep bores there. You do different stuff. They have 100 feet of very saturated clay that you can use. Capacity, what are the capacities you need of each of these different ones to meet the fluctuating power and the fluctuating usage and all that stuff? You can see it's a complex model. What's the bandwidth you need to meet the cost models and all that? How do you tune them? How much resilience do you want? In other words, how much reserve capacity do you want for this long periods? Or let's say a piece of equipment fails, pumps fail, whatever, you need to have resilience. What are the installations costs, the operation costs, the grid costs in it? And all of these together controls how fast we are going to be able to decarbonize buildings. So it's understanding how to put this all together is the critical key to rapidly decarbonizing buildings. Clearly, this is a complex model, and there's just no engineer anywhere who's going to sit down and design with this level of complexity involved. So this is why, it requires this level of design to do it. And this is why we are working with the D Lab at MIT and developing an interactive HVAC decarbonization decision support tool. It's a high-level tool to let even lay people in a style of inroads. You should check this out, this inroads style thing. It's a single-page interactive simulator where you put in all these, you select your weather, you load your building data, even if it's just from bills, from monthly bills, or whatever it is you've got. And you model the building, it models the building for you, and then you can project different kinds of combinations of these batteries to get a tuned result. Of course, we're going to add AI as soon as we can to get this right. That's what it requires. It requires developing that. That's what we're out there trying to do. Needless to say, it's complex. This is what's needed. We're not going to get to the zero carbon world quickly and cost effectively without this level of understanding of HVAC. Unless you just go to geothermal heat pumps and you do it right. Unfortunately, a lot of people don't do them right. So the one thing you really want to know is you want to have experts involved in this. None of these are simple. Make sure you have experts involved that have the specific knowledge about what they're doing, especially in geothermal. A lot of engineers have never taken the certified geoexchange designer course. They don't know what they're doing, and they screw these things up. It's unfortunate. Thank you.